Hello. We will wait for 10-15 minutes to join everyone and then we will start. Okay. Hello, I guess I am audible. Yeah. So good evening, everyone. So my name is Abhishek Munshi. So I'm a PMRF research scholar at IIT Jaipur. So I'm going to discuss today about the electrical machines, caught transformer, and a little bit about the power parallel operation of the transformer. So this is the link for the previous classes and the PPT link where you can find the notes of the previous classes. So today we will mainly discuss caught transformer and parallel operation of single phase transformers. Fine. So moving to the topic. So what is a Scott transformer basically? So a Scott transformer, we from the note that is basically a transformer where is a method of connecting two single phase transformer to form a three phase transformer. You will see that there are two single phase transformer are connected in such a manner that it can be behaves like a three phase to two phase conversion. Or it can operate from two phase to three phase also because we are using two transformer of single phase. So basically it has two phase and you are converting that into a three phase. And so you can convert three phase to two phase and two phase to three phase. Okay. So this transformer, these two single phase transformers are connected magnetically, not electrically. As you know from the principle of transformer, that in case of the transformer, both the coils are not connected electrically. So here also it also been based on the principle of magnetism. So it has a single main transformer, another transformer which is called the teaser transformer or auxiliary transformer. The auxiliary or the teaser transformer, another one is the main transformer. So both of these transformers are used for making the spot connection. So it is better known as spot transformer connection. Okay. So here in this figure, you can see that if I zoom it a little bit, then I hope it is visible now. Okay. So from the figure, you can see that the main transformer is tapped at the connection D. So the main transformer is tapped at D, and the other connection, the B and C, are acting as a three-phase cycle. The BC and the secondary, you can see that the A1 and A2 of the trigger transformer are tapping the main transformer D. Okay. If we connect it in Scott connection, so it has a primary winding PP is basically moved all the times. It provides a tapping of 0.289, 0.5, 0.866 like this. So the tapping of the transformer should go on like this in case of Scott C connection. Okay. So this is the phasor diagram of the Scott connection. If you see that VAD, VAB, VBC, these are the basic vectors. Because if we add those things, then it will give the total voltage around it. Okay. This is basically a closed equilateral triangle where you can see. So from here, if it is an equilateral triangle, then the voltage at VBD and VDC are equal and they are in phase with VBC. Okay. Since both the transformer and single phase are trying to be in phase with three phase, but like so that's why so VBD equal to VDC, you can write it like half VDC from the law of triangle, right? Now, if you consider that this is the equation. Now, the voltage between the A and D terminal, the voltage between A and D, then write it like VBD equal to VDC. That is half VDC. So, between A and D, that is basically VA minus VD. Then write it like VAD is VAB plus VBD, right? Between A and D will be class of this one VBD and VAB. This will give the VAD. So VBD and VAB will form the VAD. And the line voltage here is VA. So you can see from here that if you write it like root 3 by 2 in case of equilateral triangle. So writing it like VL common minus half plus J root 3 by 2 plus half. So ultimately we'll get 0.866 VA. That is what I am saying over there. So now you see that the teaser transformer has a primary rating of root 3 by 2 or 0.866 of the voltage rating of the main transformer, which is here on the last line. Right? So here also you can see that if the secondary voltage of the teaser transformer is V2T, and that will lead the secondary terminal voltage of the main transformer V2T by 90 degrees, according to this picture. This is the secondary of the main and the secondary of the teaser transformer. Okay. So we can give like the turns ratio, the number of turns of the PAs by TPVA, that is equal to BPM. This is more or less similar with the normal transformer. Okay. So for keeping the voltage in turns same, you see that the primary of the teaser transformer, the number of turns in the primary would equal to H3 by 2T. That is why you can say that V2T, V2L, that is the secondary voltage of the teaser and the main transformer are equal in magnitude, but they are 90-degree apart with each other. Okay. So that is why it will result in a two-phase system. Okay. So what are the applications of this kind of transformer? This spot transformer is basically used in electric furnace installation, where it is desired to operate in two single phase together. Okay, to draw the balance load from the three-phase supply. It is also used in single phase loads such as electric train, where it is scheduled to keep the load on the three-phase system as nearly as possible. It is also used to link a three-phase system to a three-phase system with the flow of power in either direction. It can move into the three-phase side or into the two-phase side. So this is all about the spot transformer. So we will solve a problem regarding spot transformer and then we will discuss about the parallel operation. So this is a question. As I said, the spot transformers are mainly used in electrical furnace. In the question, it is given that you see that a spot connected transformer is there having the power of 11,000 line to line three-phase supply. It delivers power to two single-phase 75-volt furnaces with a power factor having 0.8 lagging. The furnace 1 is consuming 250 kilowatt, and at the same time, furnace 2 is also consuming 250 kilowatt power. The phase sequence is ABC. So we have to estimate the RMS value of the current in IA. So try it. I'm giving 5 minutes because the understanding I'm going to have to solve. So after which I will going to solve. So let me solve it for you all. So so basically, here the VAD is given as 11,000 volt. That is line to line volt. If you convert it, then it is around at an angle of 0 degree. Okay. So now the current drawn from by furnace 1, that is basically this 250 kilowatt it is given. So 10 to the power 3, the power is given. And furnace 2 had a voltage of 75, power factor of 0.8, which is minus cos inverse of 0.8. That will be the angle. Since it is a lagging, so we put minus over here. So the current IA basically 250 into the voltage by power flowing in the circuit. If you solve it, it will be around 32.803, an angle of minus 36.86. So at the next part, we're asked to calculate IB. Asked to calculate IB. Similarly, for IB, you have to calculate the furnace to current. That is also 250 into 0.3. 90 degree, since it is, as I said, that both are in 90-degree phase apart. Okay. So now try to solve IB. Given 2 minutes, I already solved this part. One part is left. Try to solve IB. Okay. The IB part should be solved in a similar way. Only the angle will be changed. So it is around minus 32.803 in angle of minus 36 by 2. So it will be finally we will get answer. The magnitude will remain same. With the case. We have to minus this one. The IB should be this total term minus of this. This equal to 806 an angle of 83.13. Since IA is divided in both the sides, so IB will be this one minus this, which is 32.803 an angle of 83.1. This question has another part. Is to calculate IC. So we have IB, IA. Now we have to calculate IC. Now, similarly, if you have to solve IC, see this question, IC will be minus of this. We are applying KCL here. The total current minus IA by. If we are applying KCL, so just put in case of IA, you have to put the values of IA, which we calculated as 8.32.803 at an angle of minus 36.865. Just replace this with this, not minus. Minus is here. Okay. If you solve it, it will be also 32.803. Angle of 23.1. Only the angle will change, the magnitude will remain more or less same. Okay. So this is how we are going to solve the spot transformer questions. So next part we are discussing is the parallel operation of a transformer. So whenever we have more than one or two transformers required for larger purpose, we used to paralleling those transformers for better operations in case of the transmission lines. We were using power system. In case of power system, then we were using parallel operations of transformer. So when we connect the primary windings of two transformers to a common supply voltage, the secondary of both the transformer to a common load, that kind of situation is called uh, parallel operation of transformer. So why we need to have parallel operation? Because It is an economical method when we require a single large transformer. It's not better to choose a single large transformer other than you can use parallel transformer because if any one of the transformer can damage, you can also use it, can replace that part and you can use those other parts also. But in case of a single large transformer, there is a chance of damage, and if it is damaged, then there will be a huge massacre, right? And whenever we require extra load, we need to add more and more transformer in parallel. Okay. So basically, parallel of operation also reduce the space capacity of the substation. Since if one big transformer will require a huge space, so the substation will go rise more. So until and unless we have enough space over there, even if we have enough space over there, we don't prefer to be such kind of large transformers. So instead, we prefer to have parallel operations of transformer. We have a single phase transformer having a separate standard size, and we will do paralleling of this transformer for distribution and other purposes. Okay. And at the same time, we see that the parallel transformer connection maximizes the electrical power system availability whenever there is shutdown of the system without affecting the system performance. We can able to shut down. Suppose there are two transformers in parallel. If one of the transformer get damaged, then also we are able to get power at the end. Okay. But if we use a single transformer, if it damaged, then the whole supply will get shut down. Okay. So this is also a reason we are able to choose parallel transformers. So this is the connection. So you can see that the primary side of the transformer are connected. And it is in the supply side. The secondary sides are connected and it is in the load side. Okay. So this is the parallel connection of a transformer. Okay. So suppose A1 is the trans ratio of this transformer A, this transformer A and this transformer B. It has A1 trans ratio, it has A2 trans ratio. The equivalent impedance is Z1 here, so ZA is ZB. The load impedance across secondary is supposed to be ZA. ZA, ZA. And IA current is flowing through here. IB current is flowing through here. And we have a load of VL and IL current is flowing at the load side. Okay. So this IA will, so here in the picture, it considered IA at the load side. So consider it as the IA at the load side, IB at the load side. The total load current is IL. So it will be IA plus IB, that is equal to IA. If we consider the primary side current, then we have to convert it in by means of trans ratio. If suppose we consider the primary side current, it will be 1 by trans ratio. In the figure, it is given that the IA is in the load side, so I write it in the load side. Okay. It is in question, suppose if it is given in the primary side, then you have to calculate the secondary side. The secondary side, if you apply KCL, it will be IA plus IB, that is equal to the load. And the voltage across the load, VL, is basically this voltage, that is V1 by A1, okay, and minus IAZ or V1 by A2 minus IBZ. Okay. Both of these are correct. If you apply KVL here, you can see that this is VA by IA. If you apply KVL, then you can see that VA is equal to VA I1 minus the current flowing through is IA, that is IAZA, the potential drop over here. Similarly, it will be true for the secondary side also, for the B side. Okay. So solving both the equations, you can able to get the value of IA and IB. Just put this formula and you can able to solve the problems I will. Okay. So each of these current has two components. Here you can see that the first component represents the transformer share of the load. That is this one. This one is representing the transformer's share of the load. Correct. The second component is basically this component. The second component determining the circulating current in the secondary winding. Okay. The circulating current have some undesirable effect that it will increase the copper loss, it will overload one transformer and reduce the conventional load capacity. Obviously, if there is an increase in the current, then it will increase the I square R, I square J overall loss. So it has an inverse effect. Okay. So in parallel transformer questions, mainly you have to calculate circulating current, the load and all. Okay. So what are the conditions behind it? So the main important point, what are the conditions of parallel operation? The transformer must have same polarity. If you choose a transformer having different polarity, it will not able to connect. And the transformer should have equal turns ratio. And what are the conditions where it is not performed? Then the voltages at full load of the transformer, internal impedance should be equal. The ratio of their winding resistance to reactance should be equal for both the transformers. This condition ensures that both transformers operate at same power factor, thus sharing active power and reactive power according to their rating. This one is the major that without the same polarity it will not able to in parallel operation and it must have equal turns ratio. These are the conditions which will satisfy if, even if it's satisfied then only transformer can be in parallel. So regarding parallel operation, we will solve some questions today. And here it is given that two single phase transformers are connected in parallel. Both the transformer has these ratings and you have to calculate the no load circulating current. So just put down the formula which I given over here. Put it down, write it in your copy, and then you will be able to solve the question. Okay. So take a snap of this formula and try to solve this. I'm giving two choices. Let me solve this one. See here, the impedance of the transformer referred to LV side Z1 can be calculated as total impedance, the power at the secondary side, that is 440 voltage, that is 440, and the power, that is 300 kVA by 440. So this is basically the Z1. If we calculate it, it will be around 0.02742. Now, similarly, if we calculate the impedance of transformer 2, referring to LV, I discussed this in the previous classes, in the past two classes, how to refer. Basically, you have to multiply with the LV sides rating. So here the impedance given as say, 4 by 100, that is into, if you solve it, the Z2, the value will be around 0.0175. Therefore, the no load circulating current by Z1 plus Z2, the difference in the voltage. So if you put the value of the Z1 and Z2, you subtract it, will be around 1048 at an angle of 68.89. Finally, the answer will be 4 at an angle of minus 68.89. So this question has another part where to calculate the ohmic loss. So try it. Okay, for this part, we have to calculate the ohmic loss, right? So the ohmic loss at no load will be 414, which we calculated, square into the impedance. The impedance at transformer 2, we calculated around, uh, if we solve it, it will be 2981.988. Okay. It has another part, that is, you have to calculate the no load terminal voltage. So try to solve it and give in 2 minutes. Okay. Fine. So in this problem, we have to calculate the LV side no load terminal voltage. So as we calculated the no load terminal voltage is 440 volt. We calculated Z1 into the no load current. Fine. So we calculated the value of Z1 previously at, that is 0.00968 into the no load current, that is an angle of minus 68.91 degrees. If we solve it, it will be around 427.96 volt. So this is the next set of question where it is given that the transformer, both two transformer are given. So both the transformer has a rating of 175 kVA per unit resistance and leakage resistance. No load secondary voltage is given. So 7 for the transformer 2 is also given. So together they have to share a 700 kVA load and a 440 volt load having a power factor of 0.859. So you have to estimate the secondary side circulating current at no load. So try to solve the first part, and it has 4 parts, and it will be the last question for me. Yes, try to solve this question. Okay. Let us solve this part. Okay. So in this part, we also have to calculate the impedance. The impedance of transformer 1 is given this one. That is into the total voltage. So we transfer it into the. Now the impedance for the second transformer. Similarly, you have to convert it. Now the circulating current to calculate, as I said, the difference in the voltage by Z1 plus Z. Put it, it will be around 196.115 ampere. Okay. So this question and another part, you have to calculate the secondary current only in 5 minutes. Solve it. Fine, so let me solve this one. So here you have to calculate. So let us consider that this connected in this manner. Then so we have outside E1, E2, Z1, Z2. So the total impedance cos inverse of 0.85. So the EMF E1 will be I1 Z1 plus Z plus I2 Z. E2 will be I1 Z plus I2 of Z2 plus Z, right? So basically, if we solve it, finally get that I1 is E1 Z2 plus E1 minus E2 Z Z1 Z2 Z. Similarly, I2 is by Z1 Z2 by Z into Z1 plus Z. If you solve it, the I1 will be 496.43. So this question is another part that is you have to calculate the another current and after which, okay, try to solve this one. This will be solved with the same formula. Okay. You have to calculate I2. Hello. So this is the ninth problem. Here you have to calculate the I2. It's similar, this is the same formula you can able to solve it. The impedance 0.235 times to 0.153 by the total, which is 0.0295 ohms. It is 1004.31. In this question or the last part, you have to check that which of the conformers has cross ratings. Okay. So I'm giving 5 minutes for it. Fine. So let me solve this one. So you have to check the cross rating, right? So the transformer one, you have to calculate the rated current for transformer one. The rated current is, if you solve it, it is 397.72. Similarly, you have to calculate the rated current for transformer two. And 1250. So it's saying that the transformer one has the current is greater than its rated. Right? Transformer 2 current is less than equal to its rating. So the cross rating is okay. So I hope it's clear to everyone. If you have any doubt, you can ask me. Otherwise, we will drop the class today. Right. Okay. I hope these questions will be help you all to solve the assignment of this week. And this is all. That's all for the day. I'm going to drop the class. Good night. If you have any doubt, you can ask. Okay, fine.